spend a few minutes reviewing the stuff that we did last week here, the beginning of the electricity unit here. We talked about two types of charge, positive and negative charge. You guys remember where positive charge came from? And where, for that matter, where negative charge came from? I'm sorry? Yeah, it comes from protons and electrons, but can we be more specific than that? Are we talking about positive charge being just protons and negative charge being just electrons? If I rub a balloon against my hair and the balloon becomes positive, let's say, I'm not even sure actually whether it becomes positive or negative, doesn't matter. Okay. Let's say it becomes positive. Does that mean the balloon has just protons? No, so what does it mean then? Okay, it means it's lost electrons. Has it lost all of its electrons? Just some of them. It has more protons than electrons, right? Something with a positive charge has more protons than electrons. It's almost never going to be the case where you have just protons or just electrons. Okay, we're going to have more of one than the other, or the same number. If we have the same number of protons as electrons, by the way, what would we say? It's not positive, it's not negative, it's neutral, right? Okay, so if positive is more protons than electrons, neutral is equal number of protons and electrons, then negative, of course, is going to be more electrons than protons. Now, somebody alluded to this just a second ago. If something's going to move here, if the protons or the electrons are going to be transferred in order to charge something, right? Rub the balloon against my hair, the balloon becomes either positive or negative. Okay? Something had to move there. Charges had to move from one to the other. It's going to be what type of charge that moves from the hair to the balloon, or from the balloon to my hair? It's going to be the electrons, right? And why is it going to be the electrons that are transferring one way or the other? It's an easier transfer of charge, right? And why is it an easier transfer of charge for electrons than it is for protons? Liam? Yeah, these electrons are orbiting around the nucleus. The protons are inside the nucleus, as well as the neutrons. Now, the electrons are held by an attractive force toward the protons. They're pulled towards the protons by an electric force called Coulomb Force that we'll talk about in just a couple of days, actually. Okay, it's a force that pulls them in. Just like gravity pulls the Earth in toward the sun as the Earth orbits around the sun, and just like the moon is pulled in toward the Earth by gravity. Okay, as the moon orbits around the Earth, the electron is pulled in towards the protons. Okay, that force doesn't want to be broken, but there's a force that acts between the protons inside the nucleus called the strong nuclear force that's even bigger. So if you're going to break a force, okay, it might be hard to break any force. But if you're going to break a force, it's easier to break the weaker force than it is the stronger force. And this is the weaker force, the one that holds the electron in place. So we put a little bit of energy into it. Maybe we rub our hands together. Maybe we rub the balloon against our hair. Okay, we take some of that kinetic energy. Okay, we liberate electrons from the atom by that energy. Okay, it takes some energy to do it. Okay, but once we pump some energy into it, then those electrons, okay, we might be able to break that bond and cause those electrons to leave. If something's going to move, it's going to be electrons that leave. The unit of charge is called the Coulomb. Does anybody remember, either off the top of their head or by looking at your data sheet, what the charge of an electron is? 10 to the negative 14? No. It is 10 to the negative 19. What's the first number? The base. 1.60. Did you check your data sheet, or did you just remember that? Okay. Where do we find it on our data sheet? It is 1.6, negative 1.6 times 10 to the minus 19, but where do we find it there? Look over here under particles, all kinds of particles, some of which I recognize, some of which we don't, right? There's an electron. There's the one we want. But then it tells us the charge is minus 1e. That doesn't sound like minus 1.6 times 10 to the minus 19. So where do we find that? I'm sorry? Yeah. Under constants, we see an elementary charge, which we don't even really know what that means yet. Okay, for now, just go with it. Okay, the elementary charge is 1.6 times 10 to the minus 19. But the electron is minus 1 times the elementary charge. So minus 1 times 1.6 times 10 to the minus 19. Okay? An alpha particle, which we won't even really learn what it is until our last unit, okay, a couple of weeks before the end of class. 2e. And we could find the charge of it right away, though. It would be 3.2 times 10 to the minus 19 coulombs, because it's twice the elementary charge. All right, we also talked last week about the difference between a conductor and an insulator. Who remembers the difference? Who remembers what one of those things are? If you remember one of them, you're probably going to remember both of them, right? Who remembers what one of them is, either conductor or insulator? Travis? Okay, it doesn't inhibit the flow of electrons. It doesn't inhibit the flow of electrons. In other words, it allows the flow of electrons, right? Why does it allow the flow of electrons? Why does it not inhibit the flow of electrons? They're free to move. The electrons on the outermost regions, the outermost levels of electrons are free to move about. Okay, they're not as tightly bound in there. Okay, that's a conductor. And what are some examples, some good examples of pretty decent conductors? Generally metals, right? And we said the other day we talked about this aluminum and copper were pretty good conductors. We use copper for wiring in our houses. We used to use aluminum for wiring in our houses. Look at this. Silver. Silver is a great conductor. Another precious metal is a very good conductor as well. You know which one I'm talking about? Gold. Sometimes when you buy cables, okay, what do you notice about those cables? What does it say on the packaging? Sorry? They're gold plated. Why are they gold plated? Gold's a really good conductor, less resistance, right? Less signal loss. Okay. I'm not sure that that makes a huge difference, you know, in just plugging in the cable from your stereo system to your TV. Okay, but theoretically, it makes a bit of a difference. An insulator is something that doesn't allow electrons to flow easily. The electrons are more tightly bound, so they're not free to move around as much, at least. What are some good examples of insulators? Good insulators / poor conductors. Just because it's an insulator doesn't mean it doesn't conduct at all, right? Just means it's a bad conductor, a poor conductor. Patrick, what's an example of a good insulator? Good. Rubber's a perfect one, right? That's the one that we always think of, right? We think of it because of the rubber tires on cars, largely, right? Because lightning strikes a car, you're safe in a car because of the rubber tires. Okay, that's not the reason why you're safe in a car in a lightning storm, but that's what everybody thinks, right? So it reminds us that rubber is an insulator. Okay, rubber-soled shoes help protect us. What's another one? Wood is a good insulator as well. Okay, plastic is a good insulator. Glass is a good insulator. Normally we're talking about, if conductors are generally metals, then insulators are generally non-metals, right? Good, non-metals. And finally on Friday, Thursday, whatever day it was, we talked about the 3 laws of charge, which at some point you've heard of before. At some point you've known these before. Opposite charges attract each other. Positive attracts negative. Negative attracts positive. A positively charged balloon attracts a negatively charged wall. A proton attracts an electron. Positive attracts negative. Like charges repel each other. Okay, a negatively charged piece of plastic will repel a negatively charged piece of whatever. A positively charged balloon will repel a positively charged plastic spoon or whatever the case may be. Okay, like charges repel each other. Sorry? Be careful with that. Like poles will repel each other in magnetism, but it's 2 different phenomena here. Okay, so the laws of magnetism, you're going to learn that in the next unit actually, real similar to the laws of electricity. Opposite poles attract, like poles repel each other. Okay, but in the end, it's 2 different phenomena that are taking place there. Okay? So don't get it mixed up. Finally, the third one, charged objects attract neutral objects. Okay, objects is a key word in there, and we're going to learn a bit later on today why it has to be objects. Okay, a negatively charged or a positively charged balloon will attract a neutrally charged wall. Okay, but a proton will not attract a neutron. Okay, you can't have just individual charges and neutrons attracting each other. It's got to be objects. Okay, charged objects attracting neutral objects. Again, we'll see why a little bit later on today. Here's another law. This is new. Haven't seen this one before. It's called the law of conservation of charge. You haven't seen this in so many words before, but in the end, you could probably predict what it's going to say. The law of conservation of energy that you learned about in Physics 20 says energy can't be created or destroyed. The law of conservation of mass in chemistry says mass can't be created or destroyed. The law of conservation of momentum, for that matter, we didn't phrase it this way, but in essence it says momentum can't be created or destroyed. Okay, momentum stays the same. Momentum can't be created or destroyed. So the law of conservation of charge will also say that charge can't be created or destroyed. You can move it. Okay, when I rub that balloon against my hair, we're going to move charge. Those electrons are going to move from either the hair to the balloon or the balloon to my hair. But we're not going to create any charges, any negatives or positives. We're just going to shuffle them around a little bit. When we did the law of conservation of energy in Physics 20, there were some implications for that, right? We did a lot of questions involving the law of conservation of energy. One of the biggest type of questions that we did were those roller coaster type questions, right? Remember EI equals EF? Okay. We applied the law of conservation of energy to problems. Okay. Conservation of momentum can't be created or destroyed. Well, we applied that as well. There were some implications for that as well. Okay, in the end, it allowed us to find the final speed of car number 2 as it collided with another car, or the initial speed of this pool ball versus that pool ball. Okay, the law of conservation of charge has implications as well. We can apply that to a number of problems as well. In the end, when charge can't be created or destroyed, it allows us, among other things, to figure out what charge becomes after I touch two charged objects together. Let's say, for instance, that I don't know why that's underlined, but it doesn't matter. Say, for instance, that I touch a charge of +3 to something that has a charge of -1. Well, then I touch it to a charge of -5. After I touch them together, the charges are going to change. The total charge will remain the same because of the law of conservation of charge. But the charge of each individual object will now be different. The law of conservation of charge allows us to figure out what that charge is going to be on each individual object. Here's what we got to remember for this question and every other question like this. If you touch two objects together that have both the same charge, nothing's going to happen. Okay, you will get some electrons transferring from one to the other, but the net effect will be 0. So if I have -5 and -5, some electrons might move around, but they're still going to balance out to be -5 and -5. So no net effect, even though there's individual things moving around there. But if I touch something that's -5 and -7 together, there's going to be a net flow of charge from one to the other. They're going to try to balance out. Now, the shape of them affects that. Okay, if one is real pointy and one is more rounded, then they might not balance out quite perfectly. If one is huge and the other one is tiny, then they might not balance out perfectly. We'll assume whenever we have a problem like this, though, we'll assume that they're roughly equal size and roughly equal shape, so that if they touch each other, the charges can balance out. In other words, if -5 touches -7, what are they going to balance out to be? -6 and -6, right? We average them together. Total charge between -5 and -7 was -12. Total charge between -6 and -6 is -12. Still the same total charge, but distributed differently. Let's take a look at this one now. This one's a little bit more complicated than the one that I just gave you verbally there. This has 3 objects. Number 1, number 2, and number 3. Let's make a little chart here. Ball number 1, ball number 2, and ball number 3. We start off with +3 coulombs, which, by the way, is a gigantic amount of charge. Okay, normally, you don't see charges that are that big. I just thought in the first question we'd avoid any kind of crazy negative exponents. Plus 3, minus 1, and the third one starts off as minus 5. What's the total charge there, by the way? If we add all three of those together, what do we get? Looks like minus 3. The one thing we know here right now is that the total charge has to remain minus 3. It isn't going to change. All right, I'm going to touch 1 to number 2. Touch object number 1 to object number 2. What are they going to balance out to be? What is it going to be? Okay, no, but you're real close. You're real close. The total charge when I touch 1 and 2 together is going to be plus 2. Okay, plus 3 plus minus 1 gives me plus 2. So the total charge distributed evenly among charge 1 and 2 is going to be plus 2. So what's the charge in each one of them going to be? Cam? Plus 1. Good. Plus 1 and plus 1. Does that make sense, Travis? Okay, so you're on the right track there. You added them together. That's half the battle there. Then you just got to divide by 2. Plus 1 and plus 1. This one's going to be what? Minus 5. It hasn't changed, has it? Because we haven't touched that one yet. We'll deal with that in a little bit. Let's add these up just to make sure that I'm still good here. Plus 1, minus 5, still a total charge of minus 3. Okay, that works. Now the first one touches the third one. Plus 1 touches minus 5. The total charge between those two that are touching each other now is going to be what, Travis? Good, minus 4. Now what are they going to balance out to be if that minus 4 is distributed evenly among two charges? Max? Yeah, you know. Minus 4 distributed evenly among two different charges. Okay? Good, minus 2 and minus 2. Does that make sense, Max? All we're doing here is effectively averaging. Okay, plus 3 plus minus 1 divided by 2. Okay, add the 2 up, divide by 2. Okay, add this one and this one, divide by 2. Now what is this one, by the way? That's still going to stay plus 1, right? Let's add these up just to make sure we still have minus 3 here. Okay, minus 2 plus 1 minus 2 gives me minus 3. The final charge on all three of these objects, minus 2 plus 1 and minus 2 Coulomb. Does that make sense, guys? If we get a question like this on a test, okay, we got to get this right. Okay, right now, it might be a little bit puzzling to some of you because it's new, right? But in the end, all it involves is averaging, right? Adding and dividing by 2. Okay, literally, okay, if we taught a grade 5 kid how to do this, that all you have to do is add them and divide by 2, a grade 5 kid can do this, okay? He just has to know how to do it, that's all. The mathematics is easy. You just have to know how to do it. Good? All right, I'm gonna have you look at a couple of multiple choice questions here. First of all, multiple choice number 32. I'll ask you to submit that, please, as multiple choice number 1 on the form, please. All right, let's take a look here, guys. Interesting, the responses that I got here. We got most people, about 90% of you saying A, and the rest of you said B. B is the incorrect answer, the wrong answer, but I expected people to say B. Okay, it's not a surprise. All of the answers that you see in multiple choice are normally answers that you'll get if you make a silly little mistake, right? So where's the mistake for option B there? Why did everybody that got it wrong choose option B there? Well, we know what we got to do here, right? Okay, we got two objects. All we're going to do is add them up and divide by 2. 4.5 microcoulombs. These are microcoulombs. Doesn't really matter. Well, if we add those up, what do we get? 2.10 microcoulombs. That's exactly, Travis, what you did the very first time we did one of these problems, right? Is we added them up, and then we stopped right there. Okay, we can't stop because that's the total charge. Okay, the charge now on each individual object is that divided by 2, which gives me 1.05 microcoulombs. Does that make sense, guys? Okay, listen, okay, we all make these silly mistakes, including me. Okay, earlier today when we were going over that test question, I made one of those silly mistakes, right? Okay, just be conscious of it. The more conscious of it we are, the less likely we are to make the mistake. Doesn't guarantee that we're never going to make those mistakes, but the less likely we are to make those mistakes. So the answer is A there. Okay, one more question here. This is multiple choice or numeric response, number 33. I'd like you to submit this one, please, as numeric response question number 1. All right, let's take a look here, guys. Most people have answered here now, and most people have the correct answer as well. In fact, everybody that's responded knew what they were doing to solve this question. There was one person that filled it in incorrectly, okay, but they still knew what they were doing and still got the correct answer here. The number of excess electrons on a ball that carries a charge of minus 3.6 times 10 to the minus 19, minus 17 coulombs, expressed in scientific notation, is what? Let me give you a little analogy here, okay? There's 28 people in this room, including me, 28 people. Let's say we have the total amount of money that we have, the total amount of money that we have combined, if we count all our money up, $56. Okay, it's Monday morning. It was a big weekend of shopping and whatever. We don't have very much money left. We got $56 total between us. Right, Nick? Okay. There is $2 per person. So each of us has $2. Okay, so we got $56 and each of us has $2. How many people in the room? How do we figure that out? We got $56, each of us has $2. How many people do we have? We divide it by 2, right? We divide 56 by 2 gives us 28, right? 28 people. When we want to find a number of people, what did we do? We took the total amount of dollars and we divide it by the amount of money per person, the amount of money that each person has. Does that make sense? So the amount of money for, let's say, one person. Listen, if we want to find the number of electrons, then we're not going to take the total money, we're going to take the total charge. Okay, instead of being the total dollars, it's going to be the total charge. Instead of being the money for one person, it's going to be the charge for one electron. When you want to find a number of anything, it's going to be the total something divided by the amount for one. That makes sense? The total divided by the amount for one. So in this case, it's going to be neg 3.6 times 10 to the minus 17 divided by neg 1.6 times 10 to the minus 19. That gives us 2.25 times 10 to the 2. Now, if they asked me to express this as B times 10 to the W, my answer would be 2.25. If they asked me to express it as A decimal BC times 10 to the W, then my answer would be 225 blank. But they asked me to express it as A decimal BC times 10 to the D. So this way, we're going to express it as 225, what's the last digit? 2, right? We want that exponent in there as well. You guys see the difference between the 3 ways of expressing it? Only one of them is correct, right? And most of you said 2250. One person said 2.25, which of course means you knew what you're doing. You just expressed that wrong. Okay, let's move on here, guys. Today, our big new topic is how to charge objects. We've been talking about charge and positive charge and negative charge and which charge it is that moves. The negatives move because they're not as tightly bound to the nucleus. But what are the processes that will allow charges to transfer, electrons to move? Well, there's 2 main processes. We call them conduction and induction. Conduction conduction always involves a charge transfer. And conduction usually, not always, but usually involves touching or contact. You want to charge 2 things, touch them, Okay, that's charging by conduction. We transfer charge in that case. Induction never involves a charge transfer. That might be a little bit puzzling how we can actually charge objects without transferring charge, but we'll deal with that in a second. It never involves a charge transfer. And it never involves touching. Now we can break conduction. Okay, that's the one that we see the most often, the one that always involves charge transfer. We can break it down into two subcategories. Okay, the first one is called charging by friction. Charging by friction simply involves rubbing two things together, rubbing two objects together, transferring charge from one to the other. In order for that to happen, we normally need dissimilar objects. So let's say you've got plastic and fur, okay, or cotton and glass. Okay, two dissimilar objects. Okay, one of them will gain electrons easily, one of them will give up electrons easily. Okay, one of them is going to become negative, one of them is going to become positive. Rub them together, the kinetic energy causes the electrons to be liberated from one of them, go to the other one. Charging by contact, which sometimes we don't even call it contact, sometimes we just call it charging by conduction. The subcategory is just named the same name as the category sometimes. This simply involves touching two objects together. I'm going to put touching in quotation marks and you'll see why in a second. And then we want to balance out those charges. Or at least normally we want to balance out the charge. Okay, assuming we have the same, roughly the same size object and the same shape object, they're going to want to balance out. Why do we put touching in quotation marks? Because it doesn't always have to involve touching. Ironically, charging by contact doesn't have to actually involve contact. If I walk across the carpet with my leather-soled shoes, and then I come close to Dallin, and I stick my finger out, then he can get a shock before I actually touch him, right? That's still charging by contact. We transfer charge from me to Dallin, okay, and it transferred not because my hand rubbed against his head or his hair or whatever. Okay, it transferred because my hand got close enough to his head to be basically touching, for the electrons to jump, to arc from my hand to his head. Okay, that's also charging by contact or by conduction, even though it doesn't actually involve contact. What's the most, I shouldn't say the most common, but what's the most obvious example of charging by contact where the objects aren't actually touching? You've seen this a million times, especially when it rains. Lightning strikes, right? That's charging by contact, even though clearly the cloud isn't touching the ground. The cloud is close enough to the ground, and the air is a good enough conductor when it's moist to allow the charges to arc from the cloud to the ground, or the other way around. Charging by contact is basically, that's the example we did of conservation of charge a few minutes ago, right? That was charging by contact. You just remember that it doesn't actually have to involve touching. Usually does, but not always. But it always involves a charge transfer. Now, induction, this one's a little bit different here. Induction, we can break down into what we call a temporary separation of charge and a permanent charge. I'm going to draw a picture for this one, okay? Say we got a neutral object here. 3 positives, 3 negatives. It could be 3 billion positives and 3 billion negatives. It doesn't matter. Okay, equal number of positives and negatives. Let's bring another object nearby. Let's make it negative that we bring nearby. And I'm not suggesting that this object only has electrons. It just has more electrons than protons. So it's a negatively charged object. What's going to happen here? What's going to happen, first of all, to the protons within the neutral object, the round neutral object? What happens to the protons there? Kelsey? No, they want to. Paige, what's going to happen to them?
They stay where they are, but the electrons.
Good. The protons are going to stay where they are because they're tightly bound inside that nucleus. They can't really move, right? The protons stay where they are. But, as Paige said, the electrons don't stay where they are. The electrons are going to move away to the far side. Can anybody tell me why they're going to move away to the far side? Yep. They're going to be repelled by this negatively charged object. Look at what I have now. I still have a neutral round object. But notice now that the charges have separated so that the left side has a net negative charge and the right side has a net positive charge. That's a separation of charge. Why do we call it temporary? Why is it a temporary separation of charge? Patrick, you look like you're ready to answer there. Yeah, exactly. If I take that rectangular negatively charged object away, the electrons are just going to go back to where they were before. So it's a separation of charge right now, but it's temporary because it doesn't stay that way if I take the charging object away. This is why, by the way, charged objects attract neutral objects. Look at the side that's closest to the charging object. Here's my negatively charged object. Here's my neutral object. Logan? The side that's closest to my charging object, to my negatively charged charging object, is opposite to it. And opposites attract. Negative doesn't attract neutral because fundamentally, that's a law. Negative attracts neutral because negative attracts positive. And when we bring the negative nearby, it induces the temporary separation of charge, which allows that negative to attract the positive. Yep. No, it doesn't make it a magnet. It's a similar phenomenon to magnetism, just like the question that Tanner asked earlier on with a slightly different question, but real similar to magnetism, but it's not the same thing. Okay? Positive attracts neutral, okay? Just like a magnet will attract a regular piece of steel, but it's not for the same reason. We'll talk about why the magnetism works next unit. Okay. Let's draw another little picture here. Okay. This time we have a neutral object again. But let's bring a positively charged object nearby. Kelsey, what's going to happen to the protons in this neutral object? Nope. What's going to happen to the protons in there? Patrick? They're going to stay where they are. Protons don't move. Okay, what's going to happen to the electrons? They're going to move to the right. They're going to be pulled toward the positively charged object. Once again, we've got a separation of charge. Positive this time on the left side, negative on the right side. It's temporary because if I take this away, the electrons go back to the way they were. Again, positive attracts neutral. Why? Because the side that's closest to the positive is negative. It's oppositely charged. Okay, there's a very good chance you're going to see this question on a diploma exam in one context or another. Why do charged objects attract neutral objects? The answer is because of induction. When we induce a temporary separation of charge, the side that's closest to the charging object, okay, whether it be the positive side closest to the negative object or the negative side closest to the positive object, okay, the side that's closest to the charging object will be opposite, and opposites attract. Induction, temporary separation of charge, closest side is opposite, opposites attract. Now, last little thing here, and then we'll pretty much call it a day here in terms of new stuff. How do we make this permanent? How do we make it permanent? Keep it there? All right. Okay, fair enough. If we keep the charging object there, nothing else is going to happen, right? By the way, we're assuming the charges aren't jumping here, right? If this is close enough to this for charges to jump, this is no longer induction, right? This is contact, right? Charging by conduction. Page? Yeah. We introduce a grounding wire. This is the symbol for a grounding wire, which is literally, in most cases, a wire that goes into the ground. Although it could be anything that provides a path from the object to the ground, or that provides a path from the object to any other really, really big object that's like the Earth. What happens here? Well, the negatively charged object pushes the electrons to the far side. But if there's a wire that will allow a path to the ground, these electrons aren't going to stop there. They're going to go right into the ground, right? So these electrons that were on the left-hand side now, they were evenly distributed. Then they go to the left-hand side. Then they go into the ground. Now what do we have there? It's a positive object, right? We've charged it positive. Although if I take this away, if I take this thing away, it's just going to go back to where they were before. The electrons are going to come back up. So how do we make it permanent? We're close. I'll keep it there. Sorry? Yeah, exactly. You're going to cut the wire. Okay, we cut that grounding wire. The electrons, they want to come back up once I take this away, right? But they can't because they have no way to get back up. So now I've got a permanently positively charged object. Similar phenomenon right here. Bring the positive nearby. The electrons get sucked over to the right-hand side. More electrons get sucked up from the Earth, giving you a whole bunch of extra electrons in there. Now it's negatively charged. If I cut the wire, it's going to be permanently negatively charged because the electrons can't get back down to the Earth. So the Earth is effectively an infinite source of electrons. If we need more electrons, we can get more electrons from the Earth. But it's also an infinite sink of electrons as well. We can send as many as we want down into the Earth because the Earth is so big. That make sense? Tomorrow, I'm going to give you a couple of pretty practical applications of what we're talking about here. Okay, but real quickly, I'm going to tell you a quick little story about, two quick little stories about when I was back in university in the early 1990s. When I was, my first couple of years, I lived on campus in a dorm, which I would highly recommend for everybody for at least a year, just because it's a good experience. But then I moved out. At a certain point, it becomes enough, right? There's a bunch of guys living together. Okay, it's enough. So you move off campus. I moved off campus with 4 other guys, and we moved into this house. It was an absolute dump of a house. Like if you think you've seen, a dump of a house, okay, you have no idea. You have no idea. I promise you, you have no idea how bad this house really was. Okay. If my parents had have saw it before I signed the lease, before I actually signed a year's lease, then they probably would have never ever let me live there. It was a dump. There was no foundation in this house. Literally, the house was sitting on the dirt. Literally, okay? In fact, the house was sinking into the ground, except in the living room, in the corner of the living room, where there used to be a fireplace. So there was concrete there. That was staying where it was, but everything else was kind of sinking down around it. So if you put a ball where the fireplace used to be in the living room, it would roll like quite quickly because it was quite a slope to one corner of the living room. The stairs were about this wide. So as you're climbing up sometimes you'd fall down the stairs. Just walking up the stairs, you'd slip and fall down the stairs. Okay, the railing up top was like out of a dollhouse. Like if I'm this tall, the railing looking over down the stairs was about this high. Okay, thankfully we never fell down those stairs. The house, here's the kicker: the house wasn't even grounded. You know how most houses, well, all houses have 3-prong plugs. This had 2-prong plugs. If we wanted to plug anything in that had 3 prongs, then what we do is we bought a cheap extension cord that had 3 prongs, cut the 3rd prong off of the cheap extension cord so that it allowed us to plug in the 3-prong whatever into a 3-prong outlet, which turned it into a 2-prong outlet. But basically, it wasn't grounded, okay, which I have no idea how this house never burned down. Literally, it was torn down 2 years ago. So somehow it lasted 20 years almost after I was there. Should have been torn down before I was even there. One of the issues that we had with this house, never fire, thankfully. I don't know how we would have ever survived it if it had been a fire in that place, but thankfully there wasn't. One of the issues we had was in my grade 12 year, or sorry, in my 4th year, I had to write a thesis for my degree, and so I bought a computer, and $1,500 computer, which now would be worth about 8 cents now. I had a computer for less than a month, and it died. The hard drive crashed on the computer, and I had it literally for less than a month. Okay, and it didn't occur to me at the time why it happened, but I was telling one of my professors about it. He said, "Well, I'll tell you why it happened, because your house isn't grounded." I went, "So what?" He said, "You've got your hard drive, which is a spinning object, right? It's something that spins inside. It rubs against the air. There may be contact with something else. It charges by friction. Okay? So this hard drive builds up a charge, right? Big deal, right? Well, if your computer is grounded, it doesn't build up because it's constantly being drained, right? It's fine. But my house wasn't grounded. So what happens is the hard drive, as it spins and spins and spins, builds up a big charge, and then eventually what happens? Can't hold it anymore. Just like when the cloud builds up a big enough charge, it can't hold it anymore, and lightning strikes. So that's what happened to my computer. When it discharged, it wrecked it. It wrecked the hard drive. So thankfully, it was under warranty. I sent it back. They replaced the hard drive with, by the way, 100 megabyte hard drive. That's how big it was, 100 megabyte hard drive. Okay. Sent it back. I'm like, well, what am I going to do now? And I thought, well, I have to ground it. I can't rewire the house. So literally all I did was screwed a wire into the back of the computer, where you unscrew the case, the metal case of the computer. Okay, I attached a wire to the back of it, and then I attached that wire to our hot water heaters. There was hot water heaters in the house. That's how house was heated. Why? What did that do? Where do the hot water heaters go eventually? To the ground. So it provided the grounding wire. It did exactly the same thing as the 3rd prong would do, except it did it in a little bit more of a MacGyver type way. Didn't use chewing gum, but almost a MacGyver way. It worked fine after that. Never had a problem with it after that. Here's the other one though. One night I remember there's 4 of us sitting around a table, and then one of the guys, the 5th guy, was cooking at the stove. And so here's the stove. Here's the outside wall of the house. Okay, here's an entry area in here. Here's the fridge. Okay, and this is where the front door of the house would be, or the back door, whatever the house would be. So you'd have to, when you come in, you'd walk through here, right? And here's the kitchen. Here's the kitchen table. So there's 4 of us sitting around the kitchen table. There's one guy, the 5th roommate, who's cooking something on the stove right here. And then he gets something from the fridge. Okay, and then he goes back to the stove and whatever. He gets a shock, like just a shock, right? And he kind of jumps back and comments that he got a shock. Nobody really paid too much attention because it's just a shock, right? Then he gets another one, and then he gets another one. He's getting all these shocks. Okay, and now he's trying to figure out what it is that's causing this shock. Okay, so he's touching various parts of the stove, can't figure it out. Touching various parts of the fridge, can't figure it out. Eventually he figures out that if he touches the fridge and the stove at the same time, then he gets this shock. And what was neat about the shock was that as he touches the fridge and the stove at the same time, the shock would last as long as he touched the fridge and the stove. So if you touched it for 8 seconds, the shock would last for 8 seconds, which he couldn't do because it was a bad shock. But you know now, there's 5 guys in this house, 4 of them sitting around the table. 5 minutes ago, couldn't care less that this guy just got a shock. Now all of a sudden, even if I touch the fridge and the stove at the same time and I hold on, I keep getting a shock. So now it becomes more of a contest. More of a contest, yeah.
How long you last?
Well, initially it would last for less than a second, right? Because it's that instinct to pull back when you get that electric shock, right? But over time, over weeks, we managed to hold on for literally minutes at a time. I'm sure that it did some damage to our brains, but in that process. But you know what would happen is guys that come down the stairs, in the everybody had a different time class, right? Like, you know, I might have an 8:15 class, somebody else might have a 10:15 class. You know, first class might be 10:15, whatever. So you'd be getting up at different times. We put a piece of paper on the fridge, and it would have your name on it, and then it would say, you know, 38 seconds. And then somebody else would be like, even if you're by yourself, 38 seconds, wow. And you touch the fridge and the stove and see if you could beat that and see if you could replace the piece of paper. Of course, I was the physics student, so of course, it's all, just hold on 2 seconds, it's all coming back to me like, well, why is this doing this? And at first I had no idea. And then one day it occurred to me is that, look, the house isn't grounded. What happens? As we stand on the wooden floor, touch the fridge, everything's fine. Touch the stove, the gas-powered stove, by the way, everything's fine. Everything's fine. But when I touch the fridge and the stove at the same time, all of a sudden this fridge that's not grounded, all of a sudden has a path to the stove, which is attached by a gas line to the ground. So all of a sudden, when I touch the fridge and the stove at the same time, what am I doing? I'm grounding the fridge, right? Okay, that's it for today, guys. And we'll see you guys tomorrow.